Got another question for the AQA buffer solutions topic. So we're up to number 2 now. If you want to check out the other videos in the playlist, I'll put the link to that at the top of the screen now. Hope you like the video, hope you find it helpful, and if you haven't already subscribed to the channel, I'd love you to do so. But as always, the link to the questions in the description of the video if you want to try it first. Okay, so make a start with the first part of the question. So there's 3 bits to answer. State how the buffer can be made, give an equation for the reaction, and state how the buffer resists pH changes if you add a small amount of acid. So I'm actually going to start with the equation. So there's the equation there. For the salt, you can either show it like I've done there without the charges, or you can put the charges on. Either way is okay. So we'll move on to how the buffer is made. So the essential components of this buffer is the weak acid and the salt of the weak acid, specifically the negative ion. So how do we generate a buffer solution? We just need to make sure that there's some weak acid left at the end of the reaction. So we would partially neutralize it. And the way we do that is have the acid in excess. So moving on to the last part, state how the buffer solution resists pH changes when a small amount of acid is added. So what we need to focus on is the actual buffer system. So there's the equilibrium that's sort of at play when the buffer's working. And if you add acid to this, what you're doing is you're increasing the H+ ions. So basically what the buffer does is it uses this negative ion to react with the added H+ ions. So we just need to say something like that. The CH3CO- ion from the salt reacts with the added acid. So moving on to the calculation worth 5 marks. So the first thing we're going to need is an equation for the reaction. So there's that there. And we're going to work out the initial moles of the sodium hydroxide and ethanoic acid involved in this reaction. So for the ethanoic acid, it's just concentration times volume in decimeters cubed. And for the sodium hydroxide, it's mass over MR. MR of NaOH is 40. So the initial moles of acid, 0.5. Initial moles of sodium hydroxide is 0.05. Next thing we're going to do is work out the final moles once the reaction's happened. So you can see that the sodium hydroxide is going to be the limiting reagent because there's fewer moles of that. So they'll all go. That many moles of the acid will react. So we subtract that off the original moles and we get 0.45 that's going to be left. And in terms of the salt product, we're going to make 0.05 moles of salt because that's a limiting reagent. It's going to affect how many moles of that we can make. So we're going to get 0.05 moles of salt. I've included the H2O, but that's not actually part of this calculation. Next thing I've done is worked out the concentrations of these key components. So all I've done is taken the moles that are left at the end and divided by the volume. So they're in 0.5 decimeters cubed. So we've got 0.9 for the acid, 0.1 for the salt. Now we don't actually need to do this step, I'll explain in a second why, but I'm just going to go through the standard procedure. So we've got our concentrations now. Then we bring in our H+ concentration of a buffer is equal to acid over salt. That's what I refer to it as, so we don't forget which way around the terms go in the equation. So we've got our Ka value. It was 1.74 times 10 to the minus 5. It's listed up there in the question. There it is there. And we're going to put the acid concentration here, the salt concentration here. So that's coming out at an H+ concentration of 1.566 times 10 to the minus 4. Obviously that's going to be in moles per decimeter cubed. And then all we need to do is minus log that, and that'll give us our pH. And we've got to give our answer to 2 decimal places. So the answer is 3.81. Now I did say I'd come back to why you can use the moles rather than the concentrations. It's basically because everything's in the same volume. So you'd be dividing both of these by 0.5. So the concentration ratio is the same as the mole ratio.